Okay, well here's the formal permutation formula. P, the permutation of n things taken k at a time, is equal to n factorial on top, and not k factorial on the bottom, but n minus k factorial on the bottom. So we're going to use that. I normally don't use this form. I usually use the form we saw earlier, where I basically wrote out P in k. I write n minus 1, n minus 2, and so on, and I make sure I have k terms. So, for example, P66, it's a permutation of 6 things taken 6 at a time. Well, that one's pretty easy. Remember, the old definition said you start with 6 and you go 5, 4, 3, 2, 1 for 6 terms. And that's just 6 factorial. So let's use this formula. The first 6 is n and the second 6 is k. So what's the numerator going to be? Well, 6 factorial. What's the denominator going to be? N minus k. What is 6 minus 6? 0 factorial. So that gives us 6 factorial over 1, because remember 0 factorial is 1, so 6 factorial. And that's exactly what we had here. The old way would have been saying P73 is, you start with 7 and you do, it's basically the first 3 terms of 7 factorial. 7 factorial would go 7, 6, 5, 4, 3, 2, 1, but we're only going to write 3 terms, 7, 6, 5. Let's plug it into the formula and make sure that it works. Yeah, of course it does. P73, 7 is n and 3 is k. Remember, n always is at least as big as, let me rephrase it as k is less than or equal to 7. No, k is less than or equal to n. So using the formula, n factorial or 7 factorial goes on top. And what goes on the bottom? Not 3 factorial, but 7 minus 3 factorial, which is 7 factorial over 4 factorial. So what's this equal to? Well, the 4 factorial cancels out, so we're only going to get 765. So 7, 6, 5 multiplied together, and then I'll write 4 factorial just so I can cancel it. This is 7, 6, 5, 4, 3, 2, 1. Over 4 factorial, that cancels. 7 times 6 times 5. Same answer. Okay, write the permutation of 100 things taken 97 at a time. That one's a lot of writing if you want to write it out the long way. If you want to write out the first 97 terms of 100 factorial, well, it would look something like this. I'll use a dot, dot, dot notation, of course. 100 times 99 times 98. And I have to go all the way down to 100 minus 97 is 3. So I have to go down to one more than that, 4. 6, 5, 4. Okay, that's one way of writing it out. But using the formula above, here's our n and here's our k. So P 197 is equal to a fraction with 100 factorial upstairs in the numerator and not 97 factorial in the denominator, but 100 minus 97. 100 minus 97 in parentheses factorial. So that's 100 factorial over 3 factorial. And if the 3 factorial cancels out, notice the 3 factorial is missing from this, and that explains why. So this, well, it's exactly this. I could write, I'm not going to write it out. I'm going to stop there, but this is actually exactly what that is equal to. This would be 100 factorial, 100, 99, 98, 97, all the way down to 1. But then the 3, 2, 1 here would cancel out the 3, 2, 1 upstairs, leaving us with this, 199 all the way down to stopping at 4. Okay, last problem of the video, so take a little bit of thought. Maybe you want to stop the video and see if you can answer all 3 of these questions. A certain ID card consists of 3 uppercase letters followed by 4 digits. Remember, digits go 0 to 9, so you could have something uppercase letters. It could be A, Z, D, followed by 4 digits, followed by 1, 6, 4, 2. That would be one of the possible ID cards. Okay, so what we want to find out, if no letter and no digit can repeat. Actually, let me do a 0 here first. How many ID cards are possible? That look like this: a letter, 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 digit, 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 digit. Well, no restrictions. Another possibility, it could be AAA 1111. So it looks like that you have 26 possibilities for the first one, 26 for the next, 26 for the next, and then 10, 10, 10, 10, which we would prefer to write as 26 to the 3rd times 10 to the 4th power. That is the total number with no restrictions. That's the total number of possible ID cards right here. Now, if no letter and no digit can repeat, then how many different ID cards are possible? Well, let's see. We've got our letters there and then our 4 digits there. If no letter and no digit can repeat, how many possibilities do we have here? Well, it's a letter, 26. But I'm not allowed to reuse that letter, so it's going to be 25. And then 24. And now we get to the digits. Well, for this one, I can use any of the 10 digits from 0 to 9. That's 10. And then 9, and then 8, and then 7. So instead of 26, 26, 26, 10, 10, 10, 10, since nothing can repeat, no letter or no digit, 26, 25, 24, 10, 9, 8, 7. And you multiply those together. And again, I think I mentioned this earlier. I typically, for numbers like this that would be a pain to multiply out, you can just leave this as the answer on a quiz or a test. But you need to make sure you have the multiplication symbol between all those numbers. If you just write 26, 25, 24, it needs to be clear that you're multiplying them together. Okay, so you either put the dot or the X, or you could put each one of those in parentheses if you wanted to. All right, let's continue. If letters and digits can repeat, how many different ID cards are possible? I didn't realize that's exactly what we did upstairs at number 0. I should have just started with 1. How many ID cards are possible? From our work upstairs, we've got 26 to the 3rd times 10 to the 4th, and that's the answer. Perfectly good way to leave the answer. All right, this one shouldn't be difficult. If the letters can repeat, but digits cannot repeat, then how many different ID cards are possible? Well, it'll be similar to above. These are the letters. Letters can repeat, so what? 26 times, what's this number? 26, because they're allowed to repeat. But then the digits are not allowed to repeat, so it's going to be 10, 9, 8, 7. And this is the answer.